Okay. All right, so we'll continue our discussion on PAC learning, and we introduced a few notations last time. I hope people are still remembering the notations. If not, feel free to open up the slides. One thing I really wanted to just refresh our memory, and it's very important, is the capital R of an H. Now, the H is the hypothesis and capital R is just the true error. Or you can also say it's the generalization error. Okay, it is the error on the true distribution to evaluate this H hypothesis within a hypothesis set or hypothesis class. Okay, so that's very important. So we'll continue a discussion on PAC model. So what is a PAC model, right? So first of all, PAC learning, we all know that is probably approximately correct learning. So probably means that is with high probability. Approximately is, the learned result is very similar to the true one, but there is a little bit of an error there. So approximately correct. Okay, so what is the definition? So what is the definition of the PAC learnable? If you have a concept class C, capital C, we say that is PAC learnable if there exists a learning algorithm L, okay, such that for all small c in C, so for all target concept in the concept class, for any epsilon greater than 0, delta greater than 0, and for all distribution D, this probability of RHS smaller than equal to epsilon. So you can see why this is probably approximately correct. So probability of this true error being very small is going to be upper bounded by 1 minus delta. Delta can be really a small value, so it is almost 1. So this probability is almost 1. What probability? The probability is that it is approximately correct. So that's why it's called probably approximately correct. Okay, for samples S, so for any sample S that is drawn, that has M examples that are drawn from the distribution IID. So for any samples S of size M being a polynomial function with respect to 1 over epsilon 1 over delta. So this is very important. The M has to be a polynomial function. So the number of examples you need cannot be, for example, an exponential function with respect to 1 over epsilon 1 over delta. So that's not going to be the definition of the PAC learnable. Okay? So any questions? So you can see that this M is basically, you can think of it as a sample complexity for this algorithm L, right? And also it's kind of interesting to notice that this PAC learnable is with respect to a concept class capital C. It's also with respect to this algorithm L, right? So it talks about existence of the algorithm. You don't necessarily know the algorithm, but as long as there exists one. So this seems to be very, okay, so the question is, what is capital R? I just wanted to remind everyone again, the capital R is the true error, okay?
Wait, is capital R the expectation?
Yeah.
Okay. Sorry, and what does L produce, H?
I'll reduce H. I didn't see what your question is.
So the definition says there's an algorithm L. Does L give you H?
Okay, yeah, so there is an algorithm L that gives you H of S. So the L has to generate an H of S depending on the S. Okay? Concept class is a collection of target concepts. right? So this is talking about the algorithm works for any target concept within that concept class. We'll see an example. We'll see an example to be sure. So I wanted to first mention that concept class capital C is assumed to be known to the algorithm. Okay, so this is known to the algorithm. Also the distribution-free model, because you don't have any assumption on the distribution. It is for any distribution. So this seems to be a too strict definition, right? In practice, sometimes you only care about your performance on a certain distribution. And we will talk about that. We'll talk about the distribution related concepts later on. But this is a distribution-free model. Also, it's worth to mention that this PAC learnable definition is assuming that your training and test examples are both drawn from the same underlying distribution D, although you don't have any assumption on the D. So what that means is that if you have a transfer learning framework, this won't be applied to the transfer learning framework. Okay, so there's this probably. So again, I just wanted to emphasize that your confidence is 1 minus delta, and approximately correct, your accuracy is 1 minus epsilon. So PAC learning is not necessarily, so it's defined for supervised learning. That's true, but it could be also extended to unsupervised learning, but it would require some more thinking in terms of how do you define a target concept, okay? So for unsupervised learning, oftentimes, it's really just a density estimation problem, but how do you frame it, as a target concept is a tricky thing. For example, the example I was saying last lecture, which is like the empirical distribution estimation, right? When we talk about the martingale, that way you can think of it as a target concept, whereas the true underlying distribution is something you wanted to approximate. But again, that's very, I think it's very complicated to explain in a very short period of time. Okay. All right, so again, another thing I wanted to mention is it's very important to notice that this algorithm runs in polynomial time in terms of 1 over epsilon, 1 over delta. Polynomial time really, I mean, the sample size is m, and m is something, a polynomial function with respect to 1 over epsilon, 1 over delta. So now the natural question to ask is, what about the cost of representation of the C, right? So the representation of the concept class. So this is gonna be like a slightly modified definition of the PAC model. We're not using that in the later analysis, but I just wanted to introduce this. So there is this computational representation, basically says there is a cost for representing X within the input space. And the cost is something in the order of n. So you can imagine this is just like the input dimension, right? So it's small n. While there is also the cost of representing the target concepts, and you can say this is just order of size C, right? So extension basically means that if you wanted to have an efficient PAC learnable algorithm, it basically not only requires the sample complexity to be in the order of a polynomial with respect to 1 over epsilon, 1 over delta, also requires that preferably your sample complexity is a polynomial with respect to 1 over epsilon, 1 over delta, also a polynomial with respect to n and the size of C, right? So sometimes this is pretty important, especially for polynomial in terms of n, because n usually in the high, it is in the high dimensional space. Okay, so the big O is referring to the running time, which is the sample complexity, but it's not like the sample complexity should be written as big O. You know what I mean? It's just I'm using big O notation to represent the sample complexity. Okay. Okay. I think this is rather easy. So it's efficient, PAC, learnable. So now, some of you are confused about like the target concept, right? So, sorry, and the concept class. So we'll use the example here. So let's say we wanted to learn certain problem. What is the problem? Problem is that you learn unknown axis aligned rectangle C using as small a label. Sorry, not a label, as small a, as small a labeled sample. That's what I mean. So, the sample has to be as small as possible, but the sample is labeled. Okay, so what is the, so let me ask you this question. What is the target? Okay, let me see. What is the target concept here? It is the blue rectangle, right? It is an axis aligned rectangle. Now I'm asking you, what is potentially the concept class? Is any axis aligned rectangle, right? So my target concept is one of that, but my concept class is the selection, is the collection of the axis aligned rectangles. But let's now focus on learning one of them. So let's say the target concept is C. So then the C, basically we're letting the points within the C to be labeled as 1. Okay, so it's positive. And then C, the points outside of the C being labeled as 0. So how do we interpret this figure here, right? So these are all data points. Each of these are data. This is one data point, second data point, and so on, right? So each of these data points, so basically here I have a sample of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 examples, okay? So this is a sample of 11 examples. Apparently, this is the underlying target concept that I don't know, right? I cannot see the blue rectangle, but the label of these, examples are based on the blue rectangle. If it is within the blue rectangle, it is positive. When it's outside, it's negative, okay? Not negative, I mean 0. Is that clear? So the target concept is just to see, and the concept class is the set of all axis aligned rectangles. So then the question here is, what is your hypothesis class, right? Sometimes you don't even know the concept class. So you don't necessarily know that I have to learn a rectangle. You might learn a linear classifier. You know what I mean? For example, you're only observing these data points for a traditional machine learning problem. What do? You observe a data set, and this is just a data set, it's a sample, right? And the sample has labels, 1s and 0s. Usually you would start with a linear classifier. You don't even know what the hypothesis set should be. But now you're lucky, if someone tells you, this is just you should just use the axis aligned rectangle as your hypothesis set, H, capital H. So now you're kind of lucky. You say, oh, okay, I'm going to use that. So that's going to be my hypothesis class, H. And it's the set of all axis aligned rectangles. So then what is a hypothesis, right? So the hypothesis is any rectangle that is axis aligned, okay? So for example, if this is your hypothesis, then what happens? So let me, is there a way I can use a laser pointer? No, okay. Anyway, so this point, will be classified correctly, right? Because, you know, they are actually within, do you see what I mean? So you won't make a mistake on this h of s on these two dots, right? You won't make a mistake on these four dots either, because you would just mark them as -1, as 0, and they are actually 0. Here you will mark them as 1 and they are actually 1. Right? However, you will make a mistake here. And because you were going to mark them as 1, but they are actually 0. Also, you are going to make a mistake on these 3 blue dots because you're going to mark them as 0, but they should be 1. Okay? All right, so very simple. Now, how do you prove PAC learnable? Right? So to prove PAC learnable, you basically want to figure out one algorithm that is approximately correct. Okay, so we were talking about existence of such an algorithm. Can you come up with such an algorithm, right? So you know, to make that formal, basically it means for all C in C. So for any axis aligned rectangle in this set of axis aligned rectangles, for any epsilon, for any delta greater than 0, for any distribution D. So the distribution is, you know, the distribution, how you are generating these points, okay? So for any distribution, you wanted to make sure that the probability of the true error of HS smaller than epsilon is greater than 1 minus delta for these a small number of samples, polynomial in terms of these 1 over epsilon, 1 over delta. Okay, so this is just a reminder of the PAC learnable. Now what happens, I'm gonna consider a very simple learning algorithm, okay? So what is that learning algorithm? This learning algorithm is very simple. It just returns the tightest axis aligned rectangle, HS, that contains all the points labeled with 1, okay? So in this scenario, on this specific sample here, what you will do, you will return this H of S that I'm showing here. Is that right? Because that's the tightest axis aligned rectangle that's containing all points labeled with 1. I'm gonna return that one. And it's very important to notice this is so-called consistent rectangle. Why? Because I'm not making any mistake on this H of S, right? So the empirical error of H of S is 0. Not H of S, sorry, H sub S. Is that clear? So there is no false positive to be, you know, to be more concrete. Okay, so now the question is how large a sample? So for such an algorithm, how large should the sample be? Then the second question is, what is the probability that R of HS is greater than equal to epsilon, right? Because you wanted to prove PAC learnability. So let's see if there is any question. Sample size refers to sample cardinality. Does does complexity also refer to cardinality, or is it also capturing entropy beads required to represent? Actually, here I just specifically mean like the size of the M in this PAC learnable definition. Okay. All right, so now to prove to answer these two questions. And by the way, any other questions from the audience?
Is hypothesis class same as the concept class?
That's not correct, right? Hypothesis class is something you start with. So that's very important. That's a very good question, right? So in this example here, the concept class is just the set of all axis aligned rectangles. However, if you're unlucky, let's say, your hypothesis class could just be linear classifiers. Your hypothesis class could be just a ResNet.
So basically concept class is something which is the
underlying thing that you don't know, but well, sometimes in these analyses you would assume that you know, but usually in practice you don't know. But hypothesis class is something you assume. You as the machine learning algorithm, basically put like a prior, like some prior knowledge you believe.
Yeah, that makes sense. Thank you.
No problem. Okay. Where I was? Yeah. So to answer these two questions, first, I wanted to mention this very important concept, this probability on D of C. So what the C refers to the rectangle, the target concept rectangle, the blue C, okay? So the probability of C basically denotes the probability mass of the region defined by C. What does that mean? So you have a distribution, okay? What is the distribution? The distribution is on the input space, all right? So now you look at one region of the input space and you say, okay, I'm gonna define the probability mass on the region by probability of C on D. Does that make sense? So if you consider like a, let's say uniform probability kind of mass, then this is merely related to the area, right? However, now you have to consider the probability mass of the distribution. So it is not simply an area, it is also weighted by how important each of the area is, right? So it is kind of, how to say that? It is like weighted by the importance of that points within the area. Okay, so it's basically the probability mass of the region defined by C. So basically, as I write here, is the probability that a point randomly drawn according to D would fall within rectangle C. Okay, so if it is uniform, then the probability is just proportional to the area of this region. But now it is not, because the probability is very likely to be non-uniform. Anyway, so now we're considering one scenario, which is if the probability of C is smaller than equal to epsilon, what happens? Okay, so if that's the case, then the error of HS has force negative only, right? Because that's just the algorithm. You're returning the tightest axis aligned rectangle HS containing the points labeled with 1. So the error of HS can only have force negatives. So it is trivial to see that the probability of HS is going to be smaller than equal to epsilon. Okay? Basically, you can see from the figure here, right? It is going to be like within this. So these are the areas that you will make mistakes, right? So once you know that the probability of HS is smaller than epsilon, then it is trivial to see that R of HS is going to be smaller than equal to epsilon, because the R of HS only would count for the false positives. Okay, so this is a trivial case, right? Whenever the probability of C is smaller than epsilon, it's a trivial case. You can immediately already see that the R of HS is already smaller than equal to epsilon. So we'll focus on the more interesting scenario that the probability of C is greater than epsilon. Okay.
I think it's a little confusing, because the random variable is either 1 or 0, and the outcome
That is not true.
is,
The random variable has X and associated label. The label is either 1 or 0. The random variable is, in this special case, is just a point in a two-dimensional space. Okay, on this plate.
so when you say PR of C is less than or equal to epsilon, what does that mean?
It means the probability that a point drawn randomly according to D falling within rectangular C would have a smaller than epsilon probability.
The probability of a point being drawn in the rectangle C is less than epsilon?
Yes.
So there's no mass there. Right?
There is a very small mass.
But just looking at this picture, the points look pretty uniform. So that's why I was a little bit confused.
Oh, yeah. I mean, I cannot draw a very non-uniform points, right? I'm just drawing some random points. I am not drawing according to the distribution.
So if the points were drawn uniformly, but then they were labeled based on this rule, then what would it say? Because I was trying to imagine that.
You can just imagine this is just the probability of this region, okay? You have a density function, you're just taking the integral within this region.
But the epsilon is only compared to the error of the hypothesis. In the definition of the PAC learning. That's where I thought the epsilon came from, the definition of PAC learning.
Can we take that offline? I think we might take too much time to explain. I think it's, unless people think that is just completely unclear and nobody understands what I'm talking. Or maybe this is a good time for a breakout room. Okay, we'll try that. How do I do breakout rooms? Okay. Laura, did you join the breakout room? Okay. Jahao, Arpit, William, are you there?
Hey, Dr. Huang, I missed the beginning of class. We were the first minute. So what was the purpose of the breakout rooms? Because I joined, it joined me, but it also kicked me out right away. So I don't know if that was a bug. But what was the point of the breakout rooms?
So I think they are just discussing this what is the probability of C? I think they are confused about that. Maybe a discussion would be helpful.
Okay. I mean, that part I got, but I guess you're using the breakout rooms to allow them to talk about that like during class. That's the point of it.
Yeah.
Okay.
Yeah. I think they gave me some feedback about this. You know, they wanted to talk to each other. They didn't have the chance. So.
Yeah. Okay.
Okay. We'll give them another minute. Okay. I hope the discussion is fruitful. Anyone still have a confusion about the probability mass? So it's the probability of randomly drawing a point would fall within rectangle C. Okay? So it's literally just the probability mass of the region defined by C. Okay. I think so. It was who asked the question, was Michael or?
Oh yes, I was asking the question.
Right. Did you find the answer?
I'm more confused than ever, but we can go on.
So just imagine that you have a point, right? So, you're trying to, draw from an underlying distribution, right? So, you have a probability, there is a probability of that, once you draw from that underlying distribution, the point will be within a certain region. Right? Just think about the density of the support, on the support, right? So you're drawing from, the density function, you will get a random variable whose realization is on within the support, and in this scenario is within this C, the blue rectangle. Basically, it's just saying the probability that you draw a point, the probability of drawing the point which would end up in the rectangle is just smaller than epsilon. It's very simple. Don't overthinking it. Okay, so now let's move on. The example. So we said we wanted to focus on the probability of C being greater than epsilon. So what does that mean? Okay, so or you can, if this really confuses you, then you can imagine that I have a uniform distribution over, the support. Okay, so my underlying distribution is just uniform in this space, in this 2D space. So then this probability is really just the proportion of the area of this rectangle divided by the entire area of the support. Let's say the entire area of the support is just 1. So basically it's just the area of the rectangle. Okay, anyway, I think that's best I can do. I mean, if you're still confused, let's move the discussion to Piazza. So if epsilon is greater than 0, and you assume that the probability of C is greater than epsilon, then you can find R1, R2, R3, R4 to be 4 smallest rectangles along the sides of the rectangle C, so that the probability of these smaller rectangles are greater than equal to epsilon over 4. So let's see what that means. Okay, so yeah, I don't know what's going on with my. So this is R1. Okay, so basically we're saying that for R1, R2, R3, R4, they all have probability mass being greater than equal to epsilon over 4. Okay, so basically what do I mean by that? I don't know what's going on with my laptop. It seems like I don't have an option to go forward. Okay. All right, so what do I mean by that? So look at, you know, the rectangle C, right? It is basically defined by you know, the left and the right and bottom and the top boundary. Okay, so I can write it as, you know, square bracket L R multiply with square bracket B and T, so bottom and top. For example, you can, using this notation, you can just write R4, so this rectangle here, as, you know, the left boundary being L, which is the same as the left boundary of the rectangle C, and the right boundary being now S4, okay? And then the bottom being B and top being T. So this means is the rectangle along the side, the left side of the rectangle C. So you can define your R4 this way. So really, it is very important to see how you can find this S4 here, right? So you can find S4 such that the rectangle has a mass greater than equal to epsilon over 4. So you can find that S4. Similarly, you can do that for R1, which is to find this boundary here, R2, which is to find this boundary here, R3, which is to find this boundary here, okay? So basically, you can find that. Then what happens is that the errors can only occur in C minus HS. So the errors can only, you can only have false positives, false negatives, right?
Can I just ask, on the previous slide, the inf or the soup, what was that over? Souping over what variable? Yeah, or sorry, inf over what variable?
This is just the scalar. This just a thing. You know, this is just like, you know, it just find the boundary which gives you a mass greater than equal to epsilon over 4.
Okay.
Yeah. All right. So the error can only occur in C minus HS. So this region here I'm highlighting, right? Just because this is your algorithm, right? So now, because of the simple geometry, you would know that the error of the HS, the true error of HS being greater than epsilon would imply that HS would miss at least one region, Ri, I from 1 to 4. So R1, R2, R3. You would miss at least one region, R1 or R2 or R3 or R4, right? You know, you can prove this by contradiction. If you haven't missed any of the region, then R of HS is gonna be smaller than epsilon, of course, right?
couldn't R of HS be 0 if HS equals C?
Yes, that's true. So you can see that when RH is 0, then you're not missing any of the RIs, right? So basically you can imagine this. I'm defining these R1, R2, R3, R4, so that I can be sure that whenever my RH of S will be, the error of my hypothesis HS is greater than epsilon, I would always miss at least one of the regions. So at least one of the regions will be outside of H of S. Okay? That's a very simple like geometry argument. If you visualize this, then it's very easy to see. Now, what does this mean? This means that the probability that RH greater than epsilon will be upper bounded by the probability of this event, the union of HS misses RI, right? Based on this argument here. Right? This is again a very simple argument. Now, using the union bound, you'll see it is going to be smaller than equal to the summation of the probability HS misses RI. Right?
So is this probability over
The distribution.
S? So S is the random variable in that formula?
Yes, this is over the distribution, over the underlying distribution of your random variable.
Which is where the samples came from.
Yeah. Yeah, so it depends on the S here. Let's see if there is any question. Okay, can errors only occur in a region RI because of the probability on the previous slide? What does that mean? I'm not sure what you mean by previous slide. Do you want it to explain? Okay, CHS can be, C minus HS can be greater than union R of I. Yeah, that is true. And so the intersection is empty. What do you mean by intersection is empty? Anyway, I don't know. I cannot really understand some of the questions. I think some of you are already, getting answers from your peers. Okay, let me continue. So the probability of HS misses RI, what is this event? This means that from the sample S, all the positive points will not be within like this region, right? Any questions? So the probability of HS misses RI, how do you get that probability, right? You look at all the points that are drawn from the underlying distribution. So for each of the points, what is the probability that this point would miss RI? it's going to be 1 minus epsilon over 4, right? Because the probability that the point will be within Ri is epsilon over 4. Therefore, it misses Ri is 1 minus epsilon over 4. Okay? And now you want all of the points to miss Ri, right? So that's why you have a power m here, because these examples are IID, therefore the probabilities should be multiplicative of each other. Okay? Okay, yeah, I don't know why I'm not able to, oh, okay. All right, so set the delta greater than 0 to match the upper bound. So basically you wanted to set this quantity. Oh, by the way, I didn't mention that from here. So 1 minus x is gonna be smaller than equal to e to the minus x. Right, so due to this inequality, you will get this. Okay, so now you set the upper bound to be matching delta. So essentially you set this 4 times e to the power minus m epsilon over 4 to be smaller than delta. You will get this m. This m is going to be greater than equal to 4 over epsilon logarithm 4 over delta. So is this clear? Therefore, we can see that for m greater than equal to 4 over epsilon logarithm 4 over delta, you can see this is actually a polynomial with respect to 1 over epsilon 1 over delta. So, you know, the PAC learnable condition of m being polynomial is fine. And then you can see that for m greater than this quantity with probability at least 1 minus delta, you have this probability of the error smaller than epsilon being greater than 1 minus delta. Okay, so that's essentially the proof of this axis aligned rectangle is actually a PAC learnable concept class. There exists such an algorithm that can learn using a small number of examples, and the learning is probably approximately correct. Okay, and this algorithm here is the one that we selected, which is essentially to have the tightest rectangle that includes all the positive points. Return the tightest axis aligned rectangle containing the positive points. Okay, so any questions? This is the end of the proof. Basically, the math that's required in the proof is very simple, but the proof ideas could be a little bit tricky. It relates to geometry, and it relates to this very interesting configuration of these small r i's, r sub i's.
So I have a question.
Yes.
So I know in this specific case, we probably would not want to implement this algorithm because we'd probably not be too robust because we're going just right around the edges. So I was just kind of wondering if, that this proves that the problem is PAC learnable, but I was wondering if we sometimes have to balance the quality of the algorithm with that, or if you would have to prove it's for other algorithms. I'm not sure that makes sense.
Oh, so for this PAC learnable, remember the definition is there exists such an algorithm, right?
Right, right. I'm just wondering, if we know that at least one algorithm exists, but we still don't know if an algorithm exists that would have like properties that we would like. Maybe we would want a boundary there to make it more robust.
Yes, that is, so in terms of robustness, I think there are, it's not very clearly defined what you mean by robustness here, right? For example, in this example we show this rectangle learning, access-aligned rectangle learning, we haven't considered the scenario where your training examples could be noisy, meaning like it is actually not, the labels could be noisy, right? So for example, if you are within the rectangle, it's still labeled as 0. Or if you're outside of the rectangle, it's still labeled as 1, right? So we haven't considered that. And also, we haven't necessarily say that this is the algorithm that would achieve the highest or the most favorable complexity, sample complexity. Meaning this is the algorithm that requires least number of examples to achieve this PAC, probably approximately correct.
Okay, all right, thanks.
Yeah, so that's a very good question. So, indeed the framework haven't really focused on improving the algorithm. It is merely talking about the property of the concept class, which is the existence of the algorithm such that it could be PAC learnable.
Yep, that makes sense. All right,
Okay.
thank you.
No problem. So in conclusion, we have an infinite hypothesis set because you have infinite many number of axis-aligned rectangles. But we have a simple proof based on the concept of geometry and by a very smart construction of these smaller R sub i's and using this argument, the geometric argument to show that this is PAC learnable. But this proof, apparently is very personalized. It doesn't generalize to other scenarios, right? It is not readily applied to other similar concept classes. So then the question is, can we have more general tools to let us understand whether a concept class is PAC learnable or not, right? So then that's basically the motivation of why we wanted to learn this sample complexity for finite hypothesis set in the consistent case. Actually, we'll also learn the inconsistent case, but let's first start with the consistent case for simplicity. So the sample complexity for a finite H, so your hypothesis set has only finite number of hypotheses. And the hypothesis for simplicity is also mapping from the input space to the label space. And in this case, still, let's say 0s and 1s. And it's consistent. So what do I mean by consistent? Formally, a consistent hypothesis just means that this hypothesis empirical error is just 0 on this specific S, or the specific sample, okay? Also, the consistent case usually means that an algorithm L, that for any target concept within this, H, so that's kind of interesting, that, if IID sample S, then L actually return a consistent hypothesis with RH, or with R hat of HS being 0. So the empirical error of HS is 0. This is very interesting result, right? It has a lot of limitations, but most importantly, I want you to focus on the R hat of HS being 0. Now the generalization gap for H is essentially the upper bound on this probability here, okay? So this probability is just the supraamount of H. So you can say this is the largest gap between the true error and the empirical error. So that is the generalization gap for capital H, because capital H is the set of hypotheses, right? So you wanted to find the maximum gap within the set of hypothesis class. So you're getting like a hypothesis H, and you're taking a supraamount over the small h. Okay? Okay, so now I'm gonna ask people to think, what is the difference between these two?
So is h of s in this case in big H, so the same class as C?
Right,
Okay.
right, true. Yeah, so h of s is always in capital H because your hypothesis is always within your hypothesis set. Okay.
Okay, thanks.
Yeah. So now let's see. What is the difference between these two? Right. So first, I already talked about the interpretation of the first one. It is the probability of the largest gap within the hypothesis that is greater than epsilon, right? Whereas what is this one? This is just the probability of the specific gap for a specific sample. So it depends on the sample, right? Do you see the difference? So this H is any H. It could be any H within capital H. It doesn't have to depend on sample. It doesn't have to be generated from the sample. It doesn't have to be related to a sample and an algorithm. Whereas H of S has to be related to the sample and the algorithm that is generating the H from using the sample. Okay? So you can see the difference here. All right, so now if there is no further questions, I'll move on to the theorem here. So the theorem basically is a very powerful theorem. It says that as long as you have finite H, so the cardinality of H is just a finite number, and you're in the consistent scenario. So this is the consistent case. So then for any delta greater than 0, this RHS, so what is RHS? Is the true error of the hypothesis you generate from a sample. But remember, you're taking the probability over the samples. So overall, this counts this account for the randomness of the samples. Okay, so the probability of HS being smaller than equal to this quantity. So this is the sample complexity quantity. It's gonna be greater than equal to 1 minus delta. So what does this tell you?
So what's
okay, go ahead.
Oh, sorry, I was just gonna say it would seem that if you pick that error on the right, then you would have a requirement on M.
Exactly. So then equivalently, we're saying that for any epsilon greater than 0, delta greater than 0, the probability of the true error of any hypothesis generated from a sample using the algorithm is gonna be small. The probability of that hypothesis, the true error being small has a very high probability, almost 1, right?
Is there an assumption here that L gives a consistent hypothesis for the theorem?
Yeah, right. So when I say that is just the L would. So the consistent case is that the algorithm for any target concept within the hypothesis that you would return a consistent hypothesis. Yeah, that's a very good point. You have to make sure that it is consistent. So under that scenario, using the theorem, you can already see that this this concept class is PAC learnable. And you know exactly what's the sample complexity. Okay? So this is a very powerful theorem. This basically means that you don't have to go through all the very complicated proof we were using, for example, for this axis-aligned rectangle proof. It's simple, but it's not very generalized and also requires some careful thinking, right? So here, this seems to be like a universal solution for you to see whether a concept class is PAC learnable. And you can also come up with the sample complexity for that concept class, right? So the probability is computed over all possible samples. Yes. Yeah. Also all possible samples of size m. Exactly. So that depends on the underlying distribution D, because all the samples are all coming, IID coming from the same distribution D.
Oh, wait, I thought it was computed over the training data, or is it the test data? Or the test data, not the training data. Like the training data is the given.
So this probability of S being drawn from D to the M basically means that each sample is drawn from a, underlying distribution for M times IID.
Is
each
that
of
the
the
training?
example within the sample. Now the probability just means that, your samples are, you can imagine this is just frequency of, having all these samples, how many times you would have this error being smaller than this quantity.
So was that the training data or the test data?
This is, what do you mean by training? S is just the training data set, right? But you're measuring the probability under the true distribution.
Well, on the last example with the square, we assumed we had the points and we made the hypothesis square, and then we took the probability over S on the test data. So we assumed we had the training data.
Okay, I don't know if I understand your question.
Okay, we can move on.
Or anyone else wanted to jump in? So what I wanted to say here is this is a very powerful result. This gives you the sample complexity of an algorithm as long as this hypothesis set is finite. So what does this tell you? This is almost like telling you that if your hypothesis set is very small, this logarithm of cardinality of H is small, as long as you can find an algorithm that is consistent on all your hypotheses, then on all your target concepts, then the sample complexity is gonna be very related. So the sample complexity, as long as the log H is small, the sample complexity will be small. So basically means that in order to get a good generalization ability, you only need a very small number of examples for a small hypothesis set. So what does this mean? This means that the more simple hypothesis set you start with to train your machine learning algorithm, the fewer number of samples you need to get a good generalization ability. You don't need to you don't overfit using this small number of examples. Any questions? Okay, are we assuming H equals to C for the theorem? We are not assuming H equals to C. However, for it to be consistent, actually, in order for you to have this R hat of HS to be 0, your C has to be within H, right? So so that's a very good question, right? So let me see. So you have a C here, right? And this is the collection of the C, let's say, okay? And now if your H, let's say, is here, then your empirical error cannot be 0, because you won't, there will be some examples. If you have infinite number of examples in your sample, you will make a mistake, right? Because it's just your hypothesis H is just not included in this. Your C is just not included in your hypothesis H.
Thanks, that makes sense.
Yeah, so that means that C has to be within H for it to have an empirical error, or for it to have an empirical error 0, or for it to be consistent. So however, the thing is, say you have a C, you have the collection of the C, your H could be larger than your C, right? And that you could still have a consistent case, right? However, the problem is that you don't know how large your H could be. Your H could be very large. You just don't know, right? If your H is larger, then it's gonna be having higher. You will have a higher chance that your H would include this capital C here, right? However, the price you have to pay is that your sample complexity will be higher, because you would use larger M, H larger, than M also larger, right? The number of examples you need in your sample would be larger for you to not overfit. Okay?
That makes sense. So C just has to be contained in H for all this to work.
Yeah, true. Right, so this is just so that's why we have this hypothesis set argument here saying that, for a C within H, okay? So Juan is asking, if C is not in H, your empirical error could still be 0. I think that's, it could still be 0, but it won't be, always 0 for any sample, right? So there will be a samples that your empirical error is not 0. Okay. So is this discussion helpful?
Yep.
Okay, so this basically is like a trade-off between how large you wanted to select your H versus how complex your sample complexity is, right? So you wanted to select capital H. If it's larger, then it's more likely that you will cover the entire capital C. But if your H is very large, your M is just gonna be very large. Okay. All right. So let's move on. I'm gonna, give a very simple proof about this. So the proof idea is actually very simple. For a fixed epsilon greater than 0, we do not know which consistent hypothesis HS within H is selected by the algorithm. However, the HS depends on the algorithm that training sample S. So we need a uniform convergence bound, which is a bound that holds for the set of all consistent hypotheses. Okay, but the good news is that you are able to bound that because the number of hypotheses in a hypothesis set is just finite. So that's why, essentially the sample complexity is related to, so that's why sample complexity is related to the cardinality of H. So the proof sketch is the following. So step 1, you want to bound the probability that H within H is consistent and the true error is greater than epsilon. So you can bound that. This is gonna be like a small probability, right? And then using the union bound on finite number of hypotheses, you are able to obtain the probability that there exists such an H. So often, the event of there exists something such that this happens could be using a union bound on the opposite of that event of this thing happens. Okay. Right. So since none of these happens, then you take the union of that, then you can take 1 minus of that entire union. It will give you the existence probability. Now, step 3 is to obtain probability that any selected HS is consistent and RH is smaller than equal to epsilon. Okay, so is the proof sketch clear? So I'm gonna very quickly go through the proof, and that's gonna be the last thing we wanted to talk about in this lecture. So first, as we promised, right? So we're going to bound this probability that there exists such an H so that it is consistent, but the true error is greater than epsilon. So what is this? This basically means that I'm gonna get a union bound on like the probability of H1 being consistent and the true error greater than epsilon union H2 being consistent and the true error being greater than epsilon. So once you do this union, you will see that this will give you the probability of summation of H such that the H would have probability of the true the empirical error being 0, but the true error being greater than epsilon. Okay. So now based on because these are two, you can think about this as a joint probability because it's the end relationship between these two events. So it's essentially gonna be smaller than equal to this conditional probability, right? This is nothing but just basic probability theory. Okay, so once you have that, you can see that your probability of your probability of the empirical error being 0 conditioned on this is gonna be upper bounded by 1 minus epsilon. Sorry, give me 1 second. Here. Your probability will be upper bounded by this term. Why is that? Right? So if your true error is greater than epsilon, then for any example within this sample, the probability that you won't make a mistake on this sample is just 1, on this example is just 1 minus epsilon, right? But you have m such examples. So that's why it's gonna be 1 minus epsilon to the power m. Again, is the IID assumption you made for this examples within a sample. Right, so you get 1 minus epsilon to the power m, and again using this property that I mentioned, this 1 minus x. Let me finish this. This 1 minus x to the power m is going to be smaller than epsilon to the x. Yeah, e to the minus x. So again, you're using this property. So now the left-hand side is gonna be smaller than, so the left-hand side of this thing, right, is gonna be smaller than the right-hand side of this, which is gonna be, okay, sorry. So this one is smaller than this one, which will be upper bounded by the cardinality of H and this quantity here, right? We've already proved this quantity. It's gonna be upper bounded by the cardinality of H multiply. Yeah.
On the fourth line, to use conditional probability, don't you multiply by the probability R of H greater than epsilon?
Yeah, and the probability is going to be smaller than 1. So that's why you have the upper bound.
I see.
Oh, sorry. So that's the end of the proof. Basically, you prove that this probability will be upper bounded by this cardinality of H e to the power of minus m epsilon. So essentially, you've finished proving the theorem here. Okay. All right, so I think that's the end of today's lecture. And we do have office hours after this. So if you guys do have questions, we can use the office hour time. Okay? All right. Thanks, everyone.
Thank you.
Thank you.
Thank you.